There's a really good chance you're wearing it right now. I mean, it's everywhere, in our clothes, our houses, our cars. It's polyester. But this isn't just a story about some fabric. Nope. This is a story of some serious chemical genius, a lot of consumer frustration, and, in the end, a story of scientific redemption. So let's unravel the journey of this so-called magic material.
Okay, so let's set the scene. Our story kicks off back in the 1950s. This was an era of, post-war optimism and amazing technological marvels. And right in the middle of all this innovation, a brand new synthetic wonder was about to change fashion and, maybe even more importantly, housekeeping forever. And there it is. That was the killer marketing hook. When polyester first hit the American market in 1951, this was the promise. I mean, seriously, just imagine a world where you're constantly ironing everything, and suddenly someone offers you a fabric that looks amazing straight out of the wash. It was nothing short of a domestic revolution, all woven into a single thread. But, getting from the lab to the laundry room wasn't exactly a straight line. The initial groundwork was actually laid at DuPont, way back in the 30s, but they kind of shelved it because they were more excited about another wonder fabric, nylon. So the idea was picked up by a couple of British scientists who patented what we now call PET in 1941. It was only then that DuPont realized what they'd missed out on, and they rushed to buy back the rights to launch it as this huge commercial sensation.
So what is this magic stuff really? To get a handle on its properties, both the good and, well, the bad, we need to take a peek at its chemical recipe. And it all starts with a pretty surprising ingredient. Okay, get ready for the sciencey name. Polyethylene terephthalate, or just PET for short. And yeah, believe it or not, its journey begins as crude oil. From that, chemists extract two key chemicals, react them together, and they form these incredibly long polymer chains that eventually become polyester fiber. But how do they actually do it? I mean, what's the secret sauce? For a long time, there were actually two competing recipes for making PET. So what were these ingredients and which method ended up winning the chemical cook-off? So this right here shows a huge turning point in industrial chemistry. The original way, the DMT route, it worked, but it was inefficient and frankly dangerous. It produced flammable methanol as waste. The modern TPA route, on the other hand, is just a clear winner all around. It produces harmless water, you get a much higher yield of polyester, and the factories are cheaper to build. It's just safer, more economical, and way more efficient. A total no-brainer. The whole process really just boils down to two main steps. First step is esterification. Here, the raw materials react to create these little short chains. Think of it like making a giant pile of tiny paperclip chains that are only 2 or 3 links long. Then, in the second step, polycondensation. You take all those little chains, heat them up in a vacuum, and link them all together into the incredibly long, strong chains that make up the final PET polymer. And that's what's ready to be spun into fiber. But this is where our story takes a bit of a turn. For all of its no iron magic, the public pretty quickly discovered that the first version of polyester was, far from perfect. It actually had some really serious drawbacks. Yeah, early polyester just didn't absorb moisture at all, so it felt uncomfortable and clammy against your skin. It was a magnet for static electricity, which led to that annoying clang and even little shocks. And pilling? Oh, it pilled like crazy, forming those little fuzzballs that just ruined the look of a sweater. On top of all that, it was hard to dye, it seemed to attract oily dirt, and it was dangerously flammable. Not so magical after all, huh? So this was the big question facing the entire industry. Had they created this material with one great feature but just way too many deal-breaking flaws? Was polyester basically doomed? Absolutely not. Of course not. Science didn't just stop with the first invention. The next chapter in polyester's story is all about innovation. It's about taking every single one of those flaws and systematically engineering a solution. This is where things get really cool. First on the list, the comfort problem. So chemists figured out that by adding certain compounds, like polyalkylene ether, during the polymerization process, they could create a more hydrophilic or water-loving fiber. This made a huge difference. It improved moisture absorption, which made the fabric feel way more comfortable and cut down on all that pesky static buildup. Now, the solution for pilling was wonderfully counterintuitive. You'd think you'd want to make the fiber stronger, right? Nope. Scientists did the opposite. They made it weaker. They designed fibers with lower tenacity.
So while those little pills still form, they just break off really easily when you're wearing the garment or when it's in the wash. Pretty clever, huh? And what about those dull, boring colors? Well, the invention of cationic dyeable polyester, or CDPET, was a total game changer. By mixing in a special additive, the fiber could suddenly accept a whole new class of dyes. This opened the door to the brilliant, vibrant shades that were just impossible to get before. And to tackle the very serious issue of flammability, chemists built the solution right into the polymer's backbone. By adding phosphorus or bromine compounds directly into the chemical chain, they created a fiber with built-in flame retardancy. And because it was part of the fiber itself, it was a safety feature that couldn't just wash out or wear away. You know, this quote really captures the challenge of material science perfectly. Every single change is a trade-off. If you make a fiber less prone to pilling, you might reduce its overall strength a little bit. Improving how it takes dye could affect other properties. It's a constant, delicate balancing act, which honestly makes all these engineered solutions even more impressive. So there you have it. We've gone from a magic but deeply flawed fabric to a highly engineered, incredibly versatile material that scientists can now tailor for comfort, for safety, for style, you name it. It's a journey that just perfectly shows the power of science, of identifying a problem and methodically, cleverly engineering a solution. Which leaves us with one final thought. What challenge will this remarkable polymer be modified to solve next?